It's my great pleasure to introduce Michel from Heinrich Heine University in Düsseldorf. And Jan will be speaking to us today about LLMs in scientific discovery, proxy, partner, or pioneer. Thank you so much for being here with us. Thank you for your patience. Um, and I very much hope that your experience will be such that you will be able to sleep soundly in the coming days. So thanks so much. Please take it.
Thank you, thank you. And before I start, I would like to thank the organizer of this wonderful series, of conference, and I'm delighted to be in this great event. Thanks for this. And so what I'll present today is, well, let's call it an experiment. I'm putting together different kinds and lines of thinking into new things. And I'm looking forward to learn from you what you think about that as well. So some things are well developed, some are rather underdeveloped, and all of the stuff, mostly all of it, is pretty new. So, and before I start skipping on the slides, I would like to say that scientific discovery is one of my research topics. This is a topic I've been working on for quite some time. And now I'm wondering, can LLMs help us in any way in doing scientific discoveries? And I hope that I can shed some light on some detailed questions, maybe not answer the big ones, but a little more light to that. Okay, no, this doesn't work. Oh, it does. Yeah. So first of all, why do scientific discoveries matter? I think here's an obvious reason for that. We have doesn't really work very well. So this is from an internet site on the Grand Challenges Initiative. You don't have to read that, you can just go to that site. It's an interesting project, you find it in different, on different continents. It goes back, the term Grand Challenges goes back to mathematics, and it was reused by Bill Gates for a great health initiative. So the idea is that we as humanity, we are facing grand challenges in so many areas. And this is also very well documented in the so-called Sustainable Development Goals. So you've seen this probably before. So these are the 17 sustainable, so-called SDGs. And so you have no poverty, zero hunger, reduced inequalities, life on land, life below water, climate action, and so forth. And I think everything that's on the list rings a bell, especially in the world we live in today. So this is, I think, pretty obvious why we should be interested in scientific discovery, but I still try to make an argument from it. So why does scientific discovery, why do scientific discoveries matter? Well, first of all, in order to answer the pressing questions of humanity, be it related to climate change and its effects, protecting ecosystems, ending poverty and hunger in the world, promoting global health and education, and promoting peaceful societies, we need inventions, we need innovations, and we need breakthroughs. For the relevant inventions, innovations, and breakthroughs, we need scientific progress. And when I'm speaking of science here, well, being a German, I have the term Wissenschaft, the German term for science, in the back of my head, which is a much broader notion than the English term. So it's not only the natural sciences like physics, biology, and so forth, but also the humanities. So archaeology is in the game, and musicology, cultural studies, everything is welcome to be a science. We have to talk about that, of course. So not everything, like we still don't want to include pseudoscience or non-science there, but it's a much broader concept, and we need progress in all these fields. As you could tell if you have ever encountered the field of environmental humanities, you have a lot of progress in that field too. So progress is to be made in science. What constitutes scientific progress? In my view, what's constitutive of scientific progress is new scientific knowledge. This is currently under debate. There is a debate, if you may or may not know, about scientific progress, and there are different views on that. I take the knowledge view. Well, this is not an important thing in this argument, but I think of scientific knowledge, again, in a broad sense, Well, and how do we get scientific knowledge? Well, I think a key role is played by scientific discovery. How else? That's the argument. And here we have some typical examples just for a warm-up. Here are some examples of discovery cases you find in history, like Archimedes, or in the lower left corner you see the discovery, I think, of Uranus. Then you have an archaeological discovery. This is the blue stones they found in the, I think, Greenland or somewhere, and these are Venetian beads, and they found that people from Venice must have traveled by ship there earlier than Columbus did. So these are interesting discoveries. You have the Higgs boson, then you have a cave-like situation over there. This is where the Qumran or Dead Sea Scrolls were found, also non-natural science discovery. Oh, what's going on here?
Yeah, that's fine.
Okay. There's the DNA structure. So you have discoveries from different fields of science. Some are well known, some are old, some are new, some are breakthroughs, like the DNA double helix structure you see there, or you see Alexander Fleming discovering penicillin. And you also have things like in the middle, this is one of my favorite examples. This is actually the fish that I started with when I started thinking about discovery. Which do you still know the name?
I don't know.
Our friend.
It's an anglerfish.
It's a deep sea anglerfish, even not a shallow sea anglerfish. I have no idea about anglerfish, but this got me started. It's Lasiognathus dinema, a very tiny and really not that important discovery, apart from myself, because for me was very important. However, today we also have other discoveries we haven't seen before. And if you look in the history of science, you would not find these kinds of things. These are very new, and I think you have heard of that. So this is AlphaFold. AlphaFold, I wouldn't be able to tell you the details of that, but you can find that AlphaFold is a deep learning system developed by DeepMind that accurately predicts the 3D structures of proteins from their amino acid sequences, solving the long-standing biological challenge and accelerating research across the life sciences. And this is documented by the Nobel Prize in Chemistry in 2024 for the 3 persons who came up with this. And it's, I think currently they have AlphaFold 3, and it was AlphaFold 2 that got the Nobel Prize. So you just, in a way, I think that the idea is you feed amino acid sequences in there, and then it does all the prediction. Just for the back of your head, it becomes important later. Here's another one. You may have heard of that one too. Or if I may ask, has anyone heard of you from AlphaFold? Okay, cool. And who has heard about Alpha Tensor? Okay, this is even more amazing, and I have even less knowledge about that. I know that Alex has a background in mathematics, so it may ring a bell with you. An AI system, Alpha Tensor, from DeepMind again, that used reinforcement learning to find new, previously unknown algorithms for matrix multiplication, thereby surprisingly, that's an important word that will come back later, restructuring a decades-old mathematical problem space. This is also very new, like last year or so. If you want to learn more about that, I can recommend watch YouTube videos on that. That's pretty interesting. We saw discoveries are important for several reasons. We also have an idea what discoveries are by giving examples, but what is it really? I would like to start with a little thought experiment about discoveries, finding a new species. And since we talked about, Andrea, we talked about that earlier, I hope you don't mind if you are the key person in my thought experiment. So maybe inspired by hearing about discoveries, Andrea, after this wonderful conference, goes to the Botanical Garden of Bucharest just for leisure, but still thinking, of course, about the topic of discovery. And then he encounters some plant, a usual plant, but he sees there's 5 strange-looking beetle on it, like pink with green dots. And you collect these 5 and bring them home and wonder, maybe I'm the discoverer of a new species in biology. And as it happens, you look up the taxonomies and you find these are not in there. If they are not covered by biology. They are probably not new to nature, but if they were introduced to biology, they would be a new species. So finding a new species doesn't mean that it's new in nature, rather it's new to biology. So if you, at that moment, this is scenario 1, if you just said, wow, that's interesting, but I won't pursue that, and put these away, and nobody saw you, I would say this is not a scientific discovery. That was at best a private discovery. You learned something that no one else did. So what scenario 2 would be then is, well, you're really into that, and you call a colleague from biology, a person from coleopterology who's an expert on beetles, and you ask that person, well, I have this suspicion that these are not discovered yet. Am I right? And that person would check and double check and say, yes, we're right, I think. Shall we proceed from here? So you take pictures, make measurements, write a paper, you put exemplars of these beetles to a natural history museum, and so forth. And once your paper gets accepted, and you, of course, give a name to that, and you have in the taxonomy, you put a line to it, then your finding, what you found there in the botanical garden, counts as a new discovery in the field of biology. And in this very moment, this is my view on that, it constitutes new biological knowledge. And this new biological knowledge, in turn, is the background knowledge for later researchers in the field. So you have, I've tried to put it in a picture. The scientific background knowledge is a prerequisite for finding something. Whatever has been found, in turn, must be accepted by a relevant scientific community as a new discovery. Otherwise, it is usually a private discovery at best. Once an object of finding is accepted as a new discovery, this constitutes the case of new scientific knowledge. And new scientific knowledge, in turn, is constitutive of scientific progress. That's what I said. And I think if you look at that triangle, it makes sense. I should also say that when thinking about discoveries, I realized that I think about scientific discoveries as structured processes that are extended in time. It's not about the result, but rather of the process. This process has structural elements, some of which are essential or indispensable to the overall process, and some are not. And I think of finding, acceptance, and knowledge as the indispensable ones. Just to give an example of a dispensable or an inessential one, maybe your colleague from coleopterology uses a microscope. That could be important for your discovery, but it's not a general, indispensable structural feature of all scientific discoveries. So in astrophysics, you hardly ever use a microscope. In linguistics, you never do usually. But sometimes in biology, you use a microscope. So that's a dispensable or an inessential feature of scientific discovery. So if you have this structure, you can start doing more research on each of the components. So the acceptance part is probably the one that I debated most. So what's going on there with all these acceptance mechanisms? In biology, you have to write a paper. In other disciplines, it's different. Sometimes you have archive servers or other outlets, how things get accepted. I also have a Speech Act account, how acceptance comes about here. Also, it's not easy to say what kind of knowledge this leads to. But for today, we'll look into finding, and maybe I should say 2 words more in finding. I think of finding, and since I have chalk here, as a 2-place relation between the subject of finding and an object of finding, and finding is the relation between them, and it's an asymmetric relation because the subject of finding always finds the object of finding, but not vice versa. This is pretty simple, but I think it's a very interesting epistemological notion that is heavily understudied. I know of no epistemology textbook or so that covers the notion of finding, although it's very interesting, I think. And there's more to say on that. Maybe since I have this formula here, the subject of finding. So the overall idea is neutral to whatever the subject is. Could be Andre and Mitch together as a team, or you all as a team. Could even be a machine. And the object of finding, of course, varies too. So in biology, you discover species or mechanisms. In mathematics, you discover proofs. You can discover individual objects or methods, depending on the field you're working in. So lots of wiggle room in there. So how do scientific discoveries lead to progress? This is the picture I have in mind. Here you have the finding, that's where it starts. Well, of course, you can start from the knowledge. As I said before, it's the background knowledge. I'm starting from here because it's easier to tell the story from here. You find something that gets accepted, and this also acceptance temporally follows finding, and acceptance constitutes knowledge, and knowledge in turn constitutes progress in the field. That's the general view. I think it's compatible with other notions of progress too. That's the general view. And today, I would like not to focus on acceptance, but rather on finding. So, as you heard before, Mitch and I wrote some things, and we came up with the idea of robot cops being proxies for municipality. Are you all familiar with robot cops? No? Anyone not? Good. So just a brief background. Robot cops are in a near future machines, robots that help the municipality in question. They are driving on the hard shoulder of the highway. They're equipped with cameras and have an online connection to weather database, or what else did we have? I think statistics about accidents, stuff like that. So they drive to strategical points where many accidents could happen, and try also to catch speeders. Now it can happen that Mitch is speeding. Actually, I was the one speeding, but no, in my case, it's you. And one robot cop catches him and communicates to the other robot cop, the person with that license plate, please pull that person out of the traffic. And so Mitch is parking somewhere, and the robot cop approaches the window and acts. Yeah, well, I wouldn't tell the whole story. Just imagine an artificial cop here asking for the reasons, why were you speeding, and Mitch can give the reasons. So from this, inspired by this idea, I came to think, well, that's a nice idea to think about artificial helpers to society in the form of robot cops, but we can also have artificial helpers in science. Wouldn't that be cool to have a little assistant, like little helper, the companion of Gyro Bielus? I think it's the English term for the inventor in the Donald Duck universe. I tried to find a picture that is not copyrighted, but I think you know who I mean. And I found this fascinating. So Little Helper is around since the mid-50s and was at first only a mechanical thing. And after some time, it started really to think and have ideas and help this inventor. So I'm thinking about Little Helper LLMs now. That you can picture it as you like. It doesn't have to necessary to have a body. Can just be an LLM as we're used to. And yeah, and now I'm thinking about how can we make use of this Little Helper LLM in the context of a new finding. So first of all, some more background to finding. Whenever you find something in a scientific context, I think you need some report on what you found that has basically the form, this A is an F. So this beetle is so-and-so beetle, or take other examples. And when you have found something new and are at the beginning of a new discovery process, it's crucial to report what you've found in order to bring the process to a successful conclusion. That's the acceptance part. Now, the utterances we use to report new discoveries take the form, this A is an F, and building on Austin and a little outlandish text from Austin, actually, Maciej Witek and we just finished a paper on that, and we have analyzed this type of utterance. The result is that depending on what exactly the research context is, utterances of the form this A is an F can be understood as calling, describing, exemplifying, or classing. It's always the same very simple sentence, and here's the example. So this insect is a beetle. This is something you could say with your new finding that you have. And as you can see from these RC 1 through 4, RC stands for research context. You can have different questions. So you can ask, what can we call this insect? This insect is a beetle. So the focus is on the italics. This insect is a beetle, giving the name. Second question would be, how can we describe this insect? This insect is a beetle. Looks the same, but in this case, it's meant as a description of what you have there. Research context 3, what is an example of a beetle? This insect is a beetle. That's an example. Which of these insects classifies as a beetle? And you have several there. This insect is a beetle. So I think you got it. It's always the same sentence. This is actually more or less what Austin says, but in a different, against a different background, of course. So with the help of this, we came up with a new taxonomy of findings. And there is, before I start explaining this to you, there is two terms that you find, namely surprising and confounding, on the list in the last two columns. Surprising means here, so these terms are from Mary Morgan from a 2005 paper, and I've been using these terms. I've used them before, but have not spelled them out in detail until now. So the idea is that you can have a surprising finding. It's not about the psychological condition or so. It's rather you're a researcher in a field, say in coleopterology or whatever, and you come across something that really is surprising given the background knowledge of you as researchers. And you find this new thing and double check with your theories and find, okay, this is interesting, never expected that here, but the theories are okay with that. I just have to modify it slightly. I can introduce it with a new name to the taxonomy, or it's not falsifying the theory. While confounding findings are surprising too, but when you double check with the theory, you find, okay, this phenomenon here is really there, then the theory is completely wrong. And then you have to rewrite the theory somehow to accommodate the phenomenon. So we found that normally we have theory-guided findings. This is like normal science. What we do there is we follow the theory. We are, we systematically do our research, and we come across new phenomena, and then we describe these and we classify these. And by doing so, this also, in a way, shows that the theory is pretty good. So describing and classing is in the first column here. While surprising, and we call this theory-changing findings, are usually going with naming and exemplifying. You introduce a new name, you have new paradigmatic cases to exemplify your theoretical change that you do there. It mustn't necessarily be a great change, could also be a smaller one. However, in the confounding scenario, we found, so now it's you again, Andre. Imagine your biology colleague says, this is interesting. this looks like a beetle, or it looks beetlish. And in this case, that person would use an adjuster word. Maybe because the reason is that person knows that beetles are insects and insects have 6 legs, but your exemplar has 8. So in a way, that person could say something like, this is a beetle and it's not a beetle, but it's not on the propositional level a negation, but rather on the elocutionary level. So saying something like, the concept of beetle, it doesn't apply here. In a way it does, but we have to rethink the concept of the beetle and maybe also the theoretical background that gives us this concept. So this is the 3-part distinction that we came up with. Now back to our little helper LLMs. I was trying to find roles that they play in our research. So obviously they can be proxies, like robot cops, but in different sense proxies. Little helper LLM, so in singular here, would perform tasks like describing or classifying within established theoretical frameworks. It would contribute to finding processes by organizing and synthesizing information, but it would do so passively without epistemic commitments or initiative. So it's like what we already have. I think you can, for many of these things, you can already use well-trained ChatGPT or whatever. Then you have the role as a partner in your scientific endeavor. Little helper LLM might participate in acts like calling or exemplifying, introducing new labels or highlighting novel patterns as potentially significant, while the human researchers would remain responsible to use these notions and publish them to make them acceptable or accepted. Little helper LLM would add value by generating unexpected combinations of candidate discoveries. And the third role that appeared to me is that of a pioneer. I think in this scenario, it would be that little helper LLM would not just suggest new ideas, but actually reframe conceptual structures or challenge existing paradigms, possibly leading to major changes in the theories. This would require epistemic autonomy, I think, including norm sensitivity to the process that is going on in the discovery context, and reflective judgment. So when you ask, you want some reflection on that. So when we look at these roles and the types of scientific finding, I think we come up with this fit here. The little helper LLM role can be a proxy partner pioneer, and if it is proxy, then it's a very typical case of theory-guided finding. However, in the partner scenario, it can be a surprising theory-changing finding. So this is important that you have this partner on your side that comes up with novel insights or recombinations. In a way, you could even think of it as your, like, how did you put it? The robot postdoc or something that you have, your robot assistant, your junior partner in science, something like that. And the third role is even more, it's confounding and theory changing. So, am I still on time?
Yeah, sure.
Okay. I know everybody's hungry, so try to speed up a bit. I have different examples of types of discovery here. So for the theory guided, I'm staying with the field of biology, not only because I find this interesting, but I think, well, there are so many examples, obviously, but I think the biological examples are good for illustration here. So theory guided findings, an example of that is an ordinary species discovery, like yours. Like if you discover a new species of beetle, that's pretty normal science. It's theory guided. Well, it expands the existing classification and confirms the theory in a way. And it could also be done, I think, by little helper LLM as a proxy being involved here. However, we can also think about AlphaFold 2 or 3 or what have you, as a theory-guided finding. What AlphaFold does there solves protein folding within biophysical models, so the model stays intact. It's just the enormous amount of calculation or so that goes on there that makes it such a breakthrough. So breakthroughs can also happen in theory-guided findings, not necessarily only in confounding findings, but also here. And in this case, I think AlphaFold also serves as a proxy. And I think it's, if you look back, who won the Nobel Prize? It was the 3 humans that won the prize. It was not at all debated that the machine could get it. So, and I think this also, in a way, I feel confirmed by that the machine rather was a proxy here. However, if you look at surprising theory-changing findings, I came to think of another biological example, Tiktaalik rosea. Have you heard of that? You're right. Niels Shubin is the discoverer, and he wrote a book. Your Inner Fish became a bestseller, and it's also, I think, a Netflix series or something like that. I saw it on YouTube, I think. It's on there. And this species that he discovered is, many say it's a missing link. Well, there's a debate about what exactly a missing link is, but in a way, it is a species that has fish-like or water creature-like features and land creature-like features. And this was definitely a surprising and also theory-changing discovery. It challenged the taxonomies and extended evolutionary theory. And if it were done with a little helper, then little helper would be a partner here. And I think another example for a surprising theory-changing finding is the alpha tensor case. It's different from the AlphaFold case in that the novel matrix multiplication algorithms surprise, as I said before, mathematical domain. And so, yeah, something like a breakthrough. I think it's maybe even more than of a breakthrough than the other one, was introduced by a little helper LLM as a partner. So I think I'm almost done here. There are then 2 more examples for confounding and theory-changing findings. Actually, the first one is by my good friend Pavo Bergmann, who is a biologist in Konstanz, Germany. And he was doing his PhD on he would hesitate to call it a species of mite. When I met him for the first time and I asked what he performed research on, he would say, actually, I'm studying my own superfluousness. Because these mite biologists, I don't know how they do that, but they say they have been around for 10 million years. But for 9 million years, they have no males anymore. It's only females. That's why he said that. However, it's part of the species concept in the field of mite that you have 2 sexes for reproduction. It's part of the species. So officially, this was not a species. And he argued that must be regarded for several reasons. I won't tell you the full story, and I'm not able to. That it should be that you should change the species term here, the concept. I like the look on your face, by the way. Yeah. So the concept of species in this part of biology. So if you look at the biological species concepts that are in biology, you find that there are over 20 different species concepts. So you have different, that's quite normal, but they changed the species concept in that area of biology based on his findings here, which I think is the role of a pioneer. Well, and now I'm getting, it's hard to find other examples. I was thinking, well, nuclear fission could be an example where a new concept definitely was introduced. I came across horizontal gene transfer prions. Maybe you have other examples. It's harder to find these. These discoveries lead to conceptual disruptions rather. They undermine existing theories or models, so you have to rewrite these. But this, I think, pretty typical of a pioneer. And there's also a study by some person, I think Ritson is her name, who argued that if you have these kinds of discoveries that are disruptive, they are more likely to become breakthrough discoveries. So what we want to address the grand challenges is more breakthrough discoveries. And seemingly we need pioneers here. But actually I have the impression that we have, with our current LLMs, we can say that they are, doesn't work here.
It just needs a bit of time.
Okay. If you look at the proxy cases, I think we have these already. And I think we're getting step by step closer to the partners, so LLMs as partners in discovery. But for some reason, that's the point where I need your help. I'm really uncertain about the pioneering cases. Can LLMs be pioneers in scientific discoveries? This is basically my question. I think then I'm done here. Yeah, it says I'll leave it at that. Obviously, this is work in progress, and I would be pleased to hear your thoughts. And the question is, could our little helper LLM suitably enhanced, maybe, with a body, say, or sensory organs or something, also make confounding theory-changing discoveries? Why or why not? Thank you.
Great, thanks so much, Jan. Let's hear some questions. I see I went back in the room and then lots of questions here. Go ahead.
Thanks a lot, Jan.
I apologize. I think folks online can't really hear you. You mind? Yeah, sure.
So I had a question just about the kind of background theory of discovery that you presented. So you talked about this phrase or kind of structure to discovery, which is this A is an F, kind of like taxonomizing or classifying things. And I think that fits lots of examples of scientific discovery, but then I was trying to think of counterexamples, and it does seem like there are other cases where what's discovered is not clearly an object, but it's more like a proposition or a fact or something like that. In psychology, we find like effects. Certain people are subject to a kind of illusion under certain situations. We might find correlations between things. Maybe we discover new methods. And in many of those cases, it's not obvious that you would phrase that in anything like this A is an F, without some awkwardness. It's more, we've discovered that such and such and such. We've discovered a new way of doing this. So I don't know. Maybe I just shouldn't put too much weight on that particular way of phrasing things. But it does seem like there's an interesting division there between like discovering objects and classifying them versus discovering facts or something more abstract.
Yeah, thanks for the question. There are several things that I can say to that. First of all, this is what Austin says, IST. This is also inspired by that, so it fits very well. Austin has several reasons why he uses these letters. I'm not sure about it. You think of the problem is that the A is an individual constant, or would you prefer to have predicates involved? I'm open to that. So we leave this unspecified here. It's rather an attempt to get the general idea how we report scientific findings. By the way, findings not a discovery yet, at least not a full-blown scientific discovery. And I think we have to use that form of utterance in one way or another. But of course, it's underdetermined what we mean by A here. So of course, as I said before, the object of discovery, as I put it here, doesn't have to be a material object, can also be a species, say, or a method, or something else. What did you have in psychology?
Effects,
yeah.
correlation.
Yeah.
Yeah.
Great. Also, while we're speaking about this, it's also unclear what the is really is. Is it identity?
Yeah.
Or what is it?
Yeah.
Predication?
Yeah. Oh, thanks.
Great, good. Thanks both. Daniel?
Yeah, I have a pretty short question that comes to here. That, you said what I found very interesting was the fact that the people who build the AI that basically represents 3D the form of proteins from the amino acid chain, and there was no discussion who would get the Nobel Prize. I think that basically going to your last question, why can they be pioneers? And I think one obstacle into wanting to think about that is that we normatively do not basically give LLMs or AI any type of justice because, for example, we don't attribute them creativity, for example. We think, okay, now only humans are creative. These things are just copying pictures. They're not necessarily doing that. Or for example, if they find an ingenious solution to a coding problem, say, yeah, but it has been trained to certain net and for things. It's not necessarily an ingenious solution to this coding problem that we have. So we are having problems necessarily attributing them simpler things than paradigm changing discovery.
Yeah, I think that's a very up-to-date question because we have talked about authorship in artificial or in artificial intelligence or LLMs or what have you there. I think it's time to rethink our statutes of the prize committees. It's not set in stone that it couldn't be a machine that gets the prize. Even maybe it's more clear in the AlphaFold case than in others. But if we were to come up with a pioneering little helper LLM, why not?
Great, so that sounds great. Thanks both. Lena?
Yeah, my question also ties into that one thing you by the way, great for the talk.
Thanks.
I was just going to, do a little advocacy for AI, and there's ways to say that the fact that 3 people got the Nobel Prize instead of the actual, let's say, model shouldn't strike us as odd, considering that would be, President Donald Trump has been nominated for the prize. What I wanted to do was go a bit faster with that not talking about acceptance in this instance, because if we are going to talk about pioneering LLMs, AI models, we are in this sort of context in which even if they do have a breakthrough, it has to be accepted by humans. Might not have, kind of transparency or that are not sufficiently involved, let's say, just from a policy perspective. So, by the way, little helpers or infantilizing.
What is it?
The infantilizing.
It is just the name that is in the Donald Duck universe, so I just used that name. I didn't. Just the name. I couldn't switch that.
It's not defensive in any way. I was just trying to say that it sort of makes my point.
Yeah, so thanks. I think same answer here, and I think this is a very good point. As I just said to Daniel, we have to rethink all these things, or we can at least. So we have, you talked about acceptance, but acceptance, and I just introduced the term, by the way, acceptance mechanisms. That's how I think of the diversity of the fields of science. There's not one way of getting your paper accepted, but if you look at, say, literature, and if you look at biology and physics and other fields, it's very different. And I can well imagine that in some fields it would make perfect sense to have an AI being a reviewer, like calculating your what you have there, at least partly. So the social roles could also be fulfilled by artifacts in the end. At least I'm open to think about that. It's not something we shouldn't exclude any longer. Does that answer your question?
Anyway.
Good, great. Next up, we've got a couple of folks in the room. I think Andrea has been waiting for a while. Then we'll take the questions online, and then we'll move to you guys. Andrea.
Thank you very much for the talk. It's really fascinating.
They can't hear you. Yeah.
I will get back to AlphaFold a little bit, because I have a colleague who's molecular biology, and we have really hot debates about. The thing is, okay, the first major thing that it did is that it solved the protein folding problem. Basically, from sequences of amino acids, it projected the three-dimensional structure of the proteins, which is incredibly complicated. The sequences of amino acids are incredibly long, and it's very hard to figure out the 3D structure. And I think this was the Nobel Prize for basically for the folding.
This was AlphaFold 2.
But as things evolve, AlphaFold is now actually used for designing synthetic proteins. So basically, at this point, they do something entirely new with the system. And these synthetic proteins could be qualified as some sort of scientific discoveries, perhaps. But my question comes at this point. Okay, we have this interesting achievements, but one thing that happens here is that you actually have to trust the model. These proteins are very expensive to produce, to engineer actually. So what do? Do we trust the model, or we don't trust it to go into the acceptance phase of what we're trying with? Is trust going to become a new ingredient in this, let's say, structure of how we find, accept, and push forward scientific knowledge or not? And if trust isn't there, if we are to play to begin with, isn't AlphaFold maybe upgrading from being a proxy to being a partner?
Yeah, thanks. Lots of things I cannot answer, actually. I'm not an expert on AlphaFold. I'm not sure how the research in that field works, if they really trust, how much trust goes in there. Maybe I can give another example from 2013 or 12, when the Higgs boson was, discovered. Actually, it was a two-partite discovery. Peter Higgs said something in 1956, I think, or 58, that there is an elementary particle, and it was a theoretical thing that he did there. And the people in Switzerland, they made the experiments and gave proof to that the Higgs boson is there. But it's in the following way similar. They, in their chambers, they don't see the electrons, but rather, what do you call that? Traces, right? Traces of the electron. And they are thinking in probabilities. So they have a standard of probability when this is really there. I think this is very similar to, at this point of probability, you trust that it's there, so to speak. Maybe it's similar in your case as well. But more generally, I think trust plays a huge role in science in general, because it's a social phenomenon. We rely on each other a lot, and we try to be as transparent as possible about our achievements, our ways of thinking, and we build on others. We quote others to say, here's my sources. And this is maybe a problem with LLMs or AlphaFold or things that come from alpha, the whole alpha family. because they are not as transparent about it correctly here. Yeah, good topic, great topic, I think.
Wonderful. Thanks both. Next up, a question online from Magyona. Magyona, please go ahead.
Hello, thank you so much. This was really enjoyable. I hope it's not too noisy behind me. So I was just wondering about the pioneer role. So you said that an LLM in a pioneer role would probably require epistemic autonomy, but I didn't see exactly how that would why that would be required, right? So say that the LLM uses a theoretical framework we already have, and there's a problem with that theoretical framework, which it discovers when it tries to work with it. That would have the kind of disruptive effect that you say is the hallmark of pioneer of the pioneer role, right? But it wouldn't require any more epistemic autonomy than AlphaFold for simple chatbot, would it? We'll just use it, right? And by using it, discover the problem.
Mm-hmm. Yeah, we're getting to the heart of it here, I think. Yeah, I think what you need here, and maybe this is why I put autonomy here, is that you have to reflect on the concepts that you are trained on. And I'm not sure if you, yeah.
Why? Why would it need to reflect on it? Wouldn't it be enough to use it and thereby discover, like, you try to work with this framework and that leads you to a problem. Therefore, there must be a problem around our framework. You don't need any more reflection than that, do you?
Actually, I'm wondering, so maybe you can help me here. I was wondering if our little helper LLM can be a pioneer or not. And I was, in this case, unsure. And I'm wondering why. So that's maybe why I can't really answer your question, because I don't know.
Yeah. No, that's fair. Then we're in the same boat. Yeah.
Thanks.
Cool. Wonderful. Thank you both. Next up, Yuan, please go ahead.
Thank you. That was great presentation. I am super interested in the tripartite division there. I also want to know what kind of value do you put in what we call here the connection between hypothesis and evidence. You can have different attitudes here. You can say, oh, it's like kind of a corroboration test for different hypotheses. And in the case of AlphaFold, the way it worked originally was a contest actually to produce these results of a known protein folding, and then the AlphaFold, the software managed to develop it. But also, if you think in terms of like more falsification, I think what you have to use here is a form of getting rid of hypotheses which are not well corroborated with empirical data. So that's a form. The question is whether discovering a falsified theory, which is falsifiable, but it's just not falsified, qualifies as a form of discovery. So I'm not going back to the context of discovery and justification, but I think the ability of working on some form of coherence between hypotheses, H1, H2, Hn, and the base of data is part of this second type of interaction. I don't know if falsification is important here. It doesn't look like we should ignore it because, of course, there is a competition between different hypotheses at work. And yeah, in any case, that's the question, whether, falsification plays any role in your model.
Yeah, thanks for all these points. I said, I'm not sure if you can read the board. I said SFO here, subject of finding, object of finding. And I talked about the object of finding, saying that I'm open to a variety of things this could be, like an individual, species, a method, a proof, whatever. But I think what you implicitly say is that we discover theories. That's a way of speaking that Norbert Russell Hansen also had, but that I'm not a big fan of, actually. So from there, I would say no, we cannot discover theories, because I think we construct theories given the findings we have. Yeah, that's basically the answer to that. Maybe we just have a different concept of theory there. I think theory is not a good object for a discovery, but I may be wrong again.
Do you want to say maybe just a word more about constructing?
Constructing a theory. Yeah, well, this again depends on the field you're in. Sometimes you have to have really clear, necessary and sufficient conditions for something to be there. You have a clear grasp of what a theory in the field is, and sometimes it's more a loose term. So this is also, but in both cases, I think, or in all these cases, it's something that the community comes up with that serves a certain function, namely to explain the phenomena in question, to predict things, also to have a theoretical grasp of an understanding. But so that's why I think it's more something we construct rather, or come up with, than discover or find.
Great,
Yeah.
good. Thank you.
Thank you.
Thanks both. Next up, apologies for the rapid fire here. Lots of questions in the room. Next up, we've got Leonard. Please go ahead.
Thank you very much for the talk. That was great. So one sort of thing I was wondering is whether the notion of theory-guided discovery you have maybe can be distinguished into two different kinds of discoveries in interesting ways. One where the discovery is actually sort of directed by the theory. In the paradigmatic case, something like you have a theory, the theory makes a novel prediction, turns out that the prediction is true, and that way you discover a novel fact. And then the second, which seemed to more correspond to your beetle example, where just we do a finding, not by applying some theory, but the finding is just theoretically sort of insignificant. It's compatible with the theory, maybe in some weak sense it also confirms evolutionary theory and so on, if we find a new beetle which fits in our taxonomy and so on. And I mean, that could also be interesting to think about which kinds of LLM or deep learning guided discoveries are which kinds of theory guided discoveries. So for instance, because maybe not large language models, but at least AlphaFold and these deep learning systems are sort of not transparent and work mostly by sort of predicting based on a large number of correlations. What will happen, one might actually doubt that they can make discoveries which are directed by theories in that sense, because it just exploits statistical correlations and are not actually reasoning from theories, and then maybe it's different with large language models.
Yeah, thanks. That's a very good idea. First reaction is to ask you a question, namely, do you think this would fit in the overall picture to have two kinds of theory-guided findings?
Yeah, I mean, probably I would change the name of one of the categories.
1 and 2 or so. I was thinking while you were talking, I was thinking we have more general theories in the background, like evolutionary theory, and sometimes we have more specialized theories. So this maybe fits also with what you just said. And here's one more point inspired by what you said. I was just talking basically about LLMs because that's the topic of the conference, but of course we can think about embodied robots that comprise an LLM, but other things as well. And in many cases, when we make findings or discoveries, we need to go out there into the fields and look at the things we find in nature or wherever, in the Natural History Museum. These aspects are not covered at all. So when I talked about theory-guided findings here, I was thinking only about the things you can find by looking at the theoretical connections and without looking at the things that where you need a body, basically,
Yeah.
or an instrument even.
Yeah, I would think that AlphaFold like doesn't really look at vertical connections, right? It just looks at like statistical correlations between how, and in that sense, it's like also theory independent. But yeah, makes total sense to me.
That's right. Yeah. Yeah. Thanks.
Thank you.
Great. Thanks both. Next up, back in the room, Alex, please go ahead.
I was wondering if you have an LLM, or you have an LLM that builds Proxy, would that qualify as an LLM partner? And if you have a little helper that builds LLM partners, would that qualify as an LLM?
Good question. I think this goes into more of an engineering direction than discovery, right? So there's this LLM builds another one. Maybe we can also ask to, maybe we can rephrase what you have in mind. Can we promote LLMs to a different stage?
Yeah.
So we don't have to LLMs build each other's, but rather think of, can we promote them to become partners from proxies or so? I think it can happen. Again, depending on the field and on the conceptual capabilities of the LLM. So I think this is not like clear-cut categories, but it's rather the spectrum, and you have to, again, boring answer again, but you have to look where to use that.
Great, good. Thanks so much, Mitch.
Thanks, Jan. Two questions of clarification. One, when you talk about discoveries as being liable to produce knowledge, are you talking about individual level knowledge or sort of what we know? Think about John Hyman's paper on analytics. The distinction between what individual knows and what is known. And are you referencing one or both of those when you talk about discovery, scientific discoveries producing knowledge?
I think about both. I also I have a paper on that where I have a little chart where I make the distinctions between different kinds of knowledge. So I know that there's a debate about not the relation between knowledge that and knowledge how, but I think it's cool that we can keep the notions apart. Also, we can. It makes sense to speak about individual knowledge and institutional knowledge. And so when we make discoveries like Andre and his Beetle discovery, this leads to new knowledge in the field. So we have institutional knowledge in biology, even if all biologists, for some reason, that live today and know about his species die or so, we can still look up what happened there. It's institutionalized, it's accessible in the databases and so forth. And when you do that, it becomes your individual knowledge again, but this is not the prime aim.
Social knowledge, institutional knowledge that is carried.
Yeah. And institutional knowledge is a subcategory of social knowledge, I think.
Oh, I see. Just another request for clarification about your taxonomy, about findings. I think about cases like in my memory of the history of this design sketchy, but it's something like the discovery that very helium and mercury turned out to be a great confirmation of relativity.
Yeah.
Now that doesn't fit into any of your three general case statements because it's not business as usual. It's not surprising relative to a theory that's already accepted. It's not confounding because you already had a theory for it. It's just waiting for confirmation. So I'm wondering whether you think that should be a narrative fourth category, or whether you'd say no, it fits into one.
But I think you already gave the solution. It's confirmation, not discovery.
It's a confirmation, but it is still a discovery. It's also a discovery because it's not anything new.
Then I would think, well, I would have to look at the details. I don't know the details about that, but I think it sounds like a theory-guided finding that confirms the theory. That's what I think often happens. So we follow the lines of theory and come up with new findings in either of two senses. They're not, and this confirms the theory in a way. It's of course induction.
So maybe what you mean is that the theories in question that might be confirmed or disconfirmed might not themselves be widely accepted.
Yeah.
there could be a number of theories vying for dominance in a certain area, and discoveries might have achieved between them, but they do so in a way that is still consistent with the taxonomy.
Yeah, I think so. So it's pretty new what we did there with this taxonomy, and I'm happy to put it to the test. So one example that comes to mind is the discovery of oxygen that was like an opponent theory to phlogiston, how do you pronounce that? Theory at the time, and it was Priestley himself who discovered or isolated oxygen, but still was a phlogiston theorist. So you have two competing theories, and I think the more confirmation or data you have, the more it tends to go in the direction of the other theory.
But clarification of your taxonomy would be helpful to note that the theories in question, theory in question has been confirmed, but itself might not already be accepted. It might actually be a underdog or widely rejected by people. And the surprise is not that this phenomenon is not something that we expected, but rather we didn't expect it to confirm this controversial theory.
Yeah, but I think this is a different topic. This has nothing to do with this taxonomy that we have there. Rather, it's about confirmation in the dynamics of accepted theories in science and the overall field. We observe that all the time. So sometimes we modify theories, and then you see that different theories go together very well. And there's theoretical change and conceptual change. So this is quite a normal phenomenon. But yeah.
But it's best if the taxonomy can handle the variety of cases.
Yeah, right. That's right. But I think what you just came up with is a confirmation case. I wouldn't put it as a discovery case.
Einstein would say, yes, I was right. Everybody else had to rewrite their physics.
I think Einstein, at that point in time, he said, we don't have to conduct the experiments at all. I know it works. It's in the theory already, right? Are there experts on that here?
If so, that was hubristic.
Was that right what I said?
Yes.
No.
Okay. Yeah, right. Thanks.
Great. Awesome. Thanks so much to you all. Let's thank Jan once more.
Thank you. Great question. Thank you.
And apologies to those of you online because you won't be able to feel the deliciousness of our catering here for lunch. But looking forward to, let's say we come back in about 40 to 45 minutes, okay?
That's what, 2:15?
That's 2:30, 2:35, yeah.
Oh, yeah, right.